So let's start the afternoon session with the talk of Wooyoung Choi.
Okay, first of all, I changed the title from stability to instability. So, which means, you know, this
After this morning's talk, maybe it's rogue way.
That's right. So, anyway, this is a joint work with Roxana Tiron, who is a postdoc at the university in Korea Advanced Institute of Science and Technology. In fact, I've been there visiting, this university since last July, and since then we started, this work after I went to Korea. So this is a very recent work. So probably you might be wondering why I'm giving, this ongoing work instead of, something more complete. There is a motivation to give this talk, not the motivation of the work, but there is a cascade of length scales that Oliver talked about yesterday. So this graph shows, this is a length scale and this is a time scale, and start from 2006 to 2011, and this is exactly what where the workshops, were held in Brazil, and so.
And by the end of the week, we'll be doing quantum mechanics.
That's right.
What is the vertical scale?
So this is a centimeter length scale. So I don't know if you remember, what I talked about, many years ago. But in the first workshop, I talked about internal circulatory waves, whose length scale is order of 10 kilometers or bigger, and in terms of centimeters, is 10 to the 6, centimeter scale. And then when I came, in 2008, I talked about ocean gravity waves, and typically, the length scale of ocean waves are order of 10 meters to 100 meters. Okay, in terms of centimeters, this is this scale. And now, today, I'm going to talk about capillary waves, whose length scale is order of centimeter or smaller. So there is a very nice scaling law here. So this is a justification of why I'm talking about capillary waves. Since I hit the bottom of scale, probably this is my last visit to Brazil, unless I work on micro nano type water waves or inverse cascade. If there is inverse cascade, then I might visit again. But anyway, so this is my little motivation of this talk instead of giving a talk which is more complete. Okay. Anyway, this is my outline of my talk. So first of all, I'll just introduce Crapper solutions for capillary waves, and then I'll say a little bit about Hodograph transformation and steady extension, and then linear stability analysis, the results, and then I summarize. So the problem is very simple and well defined. So let's start with the formulation for water waves with the gravity and surface tension, and then we know this is Laplace equation is the gravity equation, and then I wrote kinematic and the dynamic free surface boundary conditions. At this point, I'm looking at 2D plane, 2D vertical plane. So in terms of wave propagation, it's one-dimensional wave propagation, and I have gravity and surface tension. So if you linearize, this problem, we know we will get a linear dispersion relation for infinitely deep water, and this is gravity term, and this is surface tension term. And if this guy is much greater than 1, then we safely neglect, the first term, which means, we can neglect, gravity, and then we have capillary waves whose restoring force is surface tension. And in terms of wavelength, for waves to be capillary waves, wavelength has to be less than 1.73 centimeters. And this time we are talking about much, smaller scale waves. So from now on, since I'm interested in very small, short wavelength waves, so we safely neglect, the gravity term, and that's what I start with. So as soon as I drop this linear term, then we have an exact solution of the Euler equations obtained by Crapper in 1957. This is I grabbed this part from JFM, and then very ingenious way Crapper found the exact solution of the capillary waves. So even though you drop the simple linear term in the dynamic free surface boundary condition, you still can get an exact solution. But if you drop complicated surface tension term, then there's no way to get the exact solution. Okay, so this is a kind of irony. But anyway, so we are looking at periodic waves. So there are this is a two-parameter family. So the parameter is wave amplitude and the wavelength. Okay. So here lambda is wavelength and the amplitude A. There is a parameter capital A, which is related to wave amplitude or wave height. So once you fix wave length, then you change wave amplitude from small value to large value, and then you get solutions like that. So this is the maximum wave amplitude you can get. So at this maximum wave amplitude, you see the bubble, or sitting at the trough, and air bubble sitting on the trough, and then there is two surfaces touch each other. Okay. And the one point that I want to make is maximum wave height. If you want to measure nonlinearity of wave, you measure nonlinearity by wave stiffness, right? So this time, the wave stiffness of the maximum wave amplitude is 0.730. As you will see soon, the maximum wave height versus wavelength for gravity waves is about 0.14. So this is 5 times steeper than gravity waves, meaning that these waves are really highly nonlinear. Okay, so you have to deal these waves in different ways. And but anyway, so this is the well-known solution by Crapper that you can get by neglecting the gravity. Okay, since we are dealing with a very nonlinear wave, so one of the way to get the exact solution is to use Hodograph transformation. As you know, we just interchange dependent and independent variables. By doing so, we can map this free surface into this physical fluid domain into a uniform strip, and then instead of psi being dependent variables, phi, psi become independent variables in this domain. So when you do that, then if you parameterize phi by Xi, or phi is C times Xi, and then automatically the stream function on the free surface is 0. Okay, which means psi doesn't change because free surface is a streamline, and also for steady problem, streamline is a material line, so kinematic boundary condition is automatically satisfied. Okay, so the only boundary condition that we have to worry about is dynamic free surface boundary condition, which is given here. Okay, so this is a nonlinear term, and this is surface tension term, and this is a Bernoulli constant for the dynamic free surface boundary conditions. And then you can get the Crapper solution from here. Or you can substitute Crapper solutions here, then you can see that the Crapper solution really satisfies this equation. Okay? And this is what the Crapper solutions that I wrote. As I said, instead of having this ugly term, if I have gravity term, which is much simpler. I don't know how to get the exact solution, okay? And then in this case, you have to solve, this equation numerically. Here, x and y, as you know, are related because they are, the harmonic conjugates. And these are the typical numerical solutions. And so this is a very small amplitude wave and then increases. And this red line represents, the maximum, the gravity wave of maximum amplitude. Okay. And as I said earlier, the wave height, which is the distance between, crest and trough, divided by lambda is 0.14. And the pure capillary waves, this ratio is 0.73. So this is really, the capillary waves are really, nonlinear waves. Okay. Now, if you want to study, a steady problem, and then you have to generalize, the Hodograph transformation. And so that is nothing but a conformal mapping between physical domain and mathematical domain here. The only problem is we don't know what the transformation is. And actually, those transformations can be obtained by imposing free surface boundary conditions. Okay. So once again, in this time, although this C is not aligned with phi and psi, okay, but you can map this domain to this, and so the only unknowns are mapping functions. And after that, you can easily solve Laplace equation in a very simple domain, and then you can solve the unsteady problem. So as I said, by using the free surface boundary conditions, you can find these unknown mappings. Okay. So first step to do that, what you need to know is a simple relationship between real part and imaginary part of a harmonic function. And there is a relationship between f and g. Okay. Real part and imaginary part at eta equal to 0, which is where the free surface is. And this H is a Hilbert transform for infinite depths. And for finite depths, the transform has a different kernel, but it's straightforward. So once we have that, then from the kinematic free surface boundary condition, this is just the change of variables, and then you end up with this, and then using this property, you can write the evolution equation for y. So this is a mapping function that we are looking for at eta equal to 0. Okay, so this mapping function gives you the free surface shape, in fact. And so when you solve this time evolution equation, then you can get the mapping function and the deformation of free surface. The problem is you don't know what the psi c is. Psi c is psi is a stream function, and therefore you need to close the system. You need one more equation, and that comes from the dynamic free surface boundary condition. Okay, so from kinematic free surface boundary condition, we got this. And for steady case, you drop this, and then actually the trivial solution is psi c is equal to 0, which means free surface is streamline. That's what we know. And also there is x, but as I said, x and y are related, so it's not a problem to write x in terms of y. So now we impose the dynamic free surface boundary conditions. Then we end up with the exact evolution equations for y and phi. Y is once again the surface elevation, and phi is the velocity potential at the free surface. And the psi and phi are related through this relationship, and the x and y are related through this relationship. Okay, so if you solve for y and phi, you know x and psi and everything. So the system is closed now. And actually this system of equations was derived by Dyachenko et al. And they really advertise this system to use. But Ovsyannikov did this derivation much earlier, although he didn't use it. But anyway, so this is something very useful if you want to study the full Euler equations in 2D. Of course, we are using conformal mapping, so this system wouldn't be applicable to 3D problem, but for 2D problem, you can write, you can solve, this system to study the evolution of nonlinear waves. So here, psi is really the parameter to represent, the free surface. So now, around this time, I started to look at this system numerically, and so we use pseudo-spectral method because I have a non-local operator H. I can easily handle the Hilbert transform in Fourier space, and therefore we use the pseudo-spectral method. And also, this time when you use pseudo-spectral method, you use only finite number of Fourier mode. So you always have a problem with aliasing errors. And in fact, there is a Jacobian sitting here. And so in terms of order of nonlinearity, it's infinity. Okay? So there is no real cutoff to eliminate the aliasing errors. So what we did is we just use some low pass filter. The details is here. And also, this system has should have conservation of physical quantities like mass, momentum, and energy. And we always monitor the conserved quantities when we solve the system numerically. When we did this work, and we are not interested in capillary waves at all, okay? We were interested in gravity waves, in fact, long gravity waves. But we want to validate the numerical code. To validate the code, what I need, the easiest thing is to compare, put the exact solution into the code and see how the exact solution evolves. And that's what we did. And so I put, I knew the Krapper solution, so I put a Krapper solution into the code, and I checked, the solution at a later time. And as I said here, at t equal to 100, I rescaled everything to 1. And then at time unit 100, the numerical solution, the error between numerical solution and exact solution is 10 to the minus 15, and which is very satisfactory, right? We also checked the conserved quantities. The order of error is same as this. So we were very happy at that point. But at some point, then I was wondering, whether these waves are stable or not. Okay, and apparently these waves are stable because we put this guy into the code. It didn't show any instability. Okay, so naturally we put many perturbations when we discretize equations. So at least since I solve I use one period, these waves are supposed to be stable to the superharmonic perturbations. In other words, perturbations whose wavelength is smaller than the wavelength of the Krapper wave. And but I just thought about it, but I didn't do anything at that time. And later, very recently, I had a conversation with Vandenbroek, and he asked me, whether this solution is stable or not, and I said I don't know. And so that's why I started to look at this problem again. And then I did some literature search for this problem. And as we know, gravity-capillary waves, there are many, nice work in the 60s and 70s. And Benjamin Ferrer, Longe Higgins, he did in 2D fully nonlinear gravity waves. And then, the many people, later extended to gravity-capillary waves and finite depth and so on. Okay? So we know a lot about, gravity and gravity-capillary waves. And when you go to the capillary waves, and then there are only two references that I could find. And one is Chen and Safman, 1985. They looked at 3D weakly nonlinear the subharmonic instability. Okay. First of all, I want to make a point that to do the stability analysis for gravity or gravity-capillary waves, you have to compute the periodic solutions first numerically. Okay. So to me, this problem is much harder than this problem. Here, at least I know the exact solution analytically, so the analysis should be easier. But the number of the papers on this is small. I mean, it's kind of understandable because the capillary waves are less practical. So probably people haven't paid attention to that. But Chen and Safman was interested in particularly 3D wave, 3D instability. And so they have to use, the physical coordinate instead of they have to work in the physical domain instead of a, transformed plane. Okay? So to do that, what they did is they rewrite the Clapeyron solutions in Fourier series in physical space, which means they could only handle small amplitude waves. Because, to handle really overhanging waves, they had to use, the component mapping, but they didn't do that because they were interested in 3D wave. So they only did weakly linear analysis of harmonic equations. This is a paper of interest. This is 2D fully nonlinear superharmonic instability. And that's what is very relevant to us. And as I said, when I solved the equation to validate the evolution code, we didn't see any instability at all. And Hogan, I don't know anyone knows this person, S.J. Hogan. Oh, you do? I'm in big trouble because I'm going to blame some of his work. So don't tell him. Right, exactly. So he did a series of works on water waves, and this is the last paper that he worked on water waves. After this, he moved to the dynamical system, and then he did completely different things. And so in his paper, 1988, what he said is basically, so what you're looking at is the wave speed of perturbation, or imaginary part of eigenvalue, or real part, depending on how you set. And then this is a steepness of Clapeyron solutions, okay? So, and sometimes, they two, the branches collide here, and then they show the growth rate. So meaning that at some wave amplitude, then we expect the instability, which is different from what my observations based on the numerical solutions. And at that time, I thought there is something going on in my numerical code, right? And because he showed there is a really instability. Also in this paper, he said we should consider subharmonic normal mode perturbations in another paper. So I thought, oh, we are done, right? We are trying to look at this instability, and this person seems to have looked at both subharmonic and superharmonic perturbations. So we tried to find this paper, but we couldn't find this paper. So we are trying to start to look for this person, and he was in Oxford at that time, and now he's in Bristol, I think. And so we sent an email to him, and we didn't know whether he's the right person because he stopped working on water waves many years ago. And we sent an email whether he's the person who did this. And he replied very quickly, actually. I was quite surprised. He said, oh, that's me. And, but I didn't publish the paper. I stopped working on water waves after this. Okay, that's what he said. So we said, oh, phew. At least we can work on this subharmonic perturbation part, which is new, okay? But at the same time, since we have a result for superharmonic perturbations, we can check our results with this paper. Okay. So we did that. But there is a little subtle difference between his stability analysis and our stability analysis. I'm not going to touch that at this point, but there is a subtle difference between two approaches. But anyway, so this is a very standard linear stability analysis. Capital letters represent Kraft solutions, and then we perturb slightly, and then we linearize the problem. And then since all the the capital letters are periodic functions, so we can use flow case theory, and then we write the solution in this form. Okay, so usual story, right? If real part of sigma is positive, and this is unstable, otherwise stable. And here there is a parameter p, and if p is 0, then it's a superharmonic perturbations, because this is periodic function in one wavelength. And if p is between 0 and 1, then the perturbations are subharmonic. Okay? So we look at the two different cases. Before we look at that, it's a standard thing, right? So we use flow case theory. So this is periodic part, and periodic part can be written in Fourier series, and then substitute these representations into the linearized equations, and then we end up with eigen solutions. Okay, eigenvalues and eigenvectors. And the eigensolutions depend on wave height of Kraft solution and the perturbation of wave number, which is p or p plus m. Okay, m is a mode number here, or j in this case. And so h equal to 0, in other words, if we collapse the amplitude of Kraft solution to be 0, then we end up with linear dispersion relation in a moving frame. And there's another thing that I might want to mention is Klein signature. Based on McKay and Softman, the Klein signature measured by this, physically this represents the energy in the moving frame. If for each mode has the unique Klein signature, and that Klein signature remains unchanged. In other words, if it is positive, even though you change h from 0 to some value. And also when there is a necessary condition for instability, in other words, if there are two mode with the different signatures, then if there is a collision between two eigenvalues of different signatures, then there might be an instability. Okay, so those are all known, and then we put it in a machinery. I'm going to present some results. So this is the picture that I showed you earlier, and this is the result by Hogan. Okay, and the black lines are the results of Hogan, and the red lines are our results. And as you can see, the Hogan claimed that the two eigenvalues collide, and therefore, instability should be there. But our computation doesn't show, collision of two eigenvalues. Okay. So we spent, quite a time to figure out what the problem is in our code, and so we couldn't do that. And so there are two particular, the amplitude ranges where the eigenvalues collide. And since we do have the evolution equation code, so what we did is we put the eigenvector into the evolution code and let it evolve. Then see whether we see the instability or not. I mean, we can do that because we have an evolution code. And I'm plotting only perturbation part. This is t equal to 0, time increases in this direction. Even though I increase the time, I don't see any instability at all. Okay? And we also compare the evolution solution of evolution code with a linear solution, and then they match very well. So no sign of instability. And then we change the parameter again. And for this, Hogan said, there is instability. We did exactly the same thing. And then we run the evolution code. There is no instability at all. So finally, we conclude that we are right, he's wrong. Okay? And also, he's not in the world wave field, so I can say anything at this point. But anyway, so then the question is why? Why we see different things? Okay? He saw instability, we saw stability. And so we read his paper more carefully, then there is a sentence like this. There is some value, which is 10 to the minus 9th. He said, values of this size cannot be resolved by our program. So it was in 1988, and so we assume he used single precision instead of double precision. Okay. I cannot increase his code to double precision, but I can reduce the precision of my code to the single precision, and then we see the very similar thing, but not exactly the same because our formulations are slightly different. Okay, we are not looking at the convergent solutions, so they don't have to match. Okay, because we have different formulations. If the solution converges, we should have exactly the same things. But anyway, so the conclusion that we have made is he used single precision computation. That's why he didn't get the right the stability curve. Also, he said, according to the work of McKay-Saffman, the two eigenvalues have opposite signature. As I said, there is a necessary condition for instability. So if two eigenvalues collide, they should have an opposite signature. Okay? And he said, they have a different opposite signature. But we realized that his interpretation of Klein's signature was wrong. And in fact, the eigenvalues he claimed to collide have the same Klein signature. Okay, so that's why we kind of believe that our results are reliable, and his results are not. Actually, we submitted this paper, so I don't know whether he will review the paper or not, but we'll see. Okay, all right. Now move to the subharmonic part. So this time, we are talking about modulation of amplitude that we talked about this morning. And in this case, the capillary waves are all unstable. Okay. So this is bifurcation diagram. And I change P goes from 0 to 1. Okay. And also it's a symmetric about P equal to 1/2. So I have to go from 0 to 1/2. And then we see the collision of eigenvalues, and they have a different opposite signatures as the necessary condition of McKay-Saffman claimed. So everything worked out, and this is a growth rate curve for different wave amplitude. So each curve represents the growth rate of different wave amplitude, and it goes all the way to 0.73. That's the maximum wave amplitude. And we zoomed in this area, and the solid line that our computations. And this, we are talking about modulation of instability. So NRS equation is very relevant here. And you can write the NRS equation for the capillary waves. And therefore, you can compare the solution of the results from NRS equation. And the amplitude is small, then they are very close. But as the amplitude increases, as we expected, NRS is for only weakly nonlinear waves. Therefore, we see it.
The Wooyoung kind of theory for, you look at the modulation of fully nonlinear travel waves, you might
No.
find that the Wooyoung equations would turn elliptic rather than the
Right. I don't know whether I can really use Wooyong's equation for the Krapper solutions in transformed plane, right? That's what I have to do, right? But here, what we actually this NRS type analysis has been done by Chen and Saffman when they looked at the stability numerically, and in this case, they use small amplitude assumption again, and as I said, they were interested in three-dimensional perturbations, and therefore they had to use the small amplitude assumption. But going back to your question, we haven't done that. Okay. I don't have the answer whether I really can do it or not, but something that we can explore. So that also confirms our numerical solutions. And then also we compare our solutions with NRS. This is the maximum growth rate. So we monitor where the maximum growth rate is. And then we compare that with NRS theory, which is a dashed dot line. And also we compare with the Chen and Safline's result, which are the numerical results. And as I said, since they use Fourier series, as you know, Fourier series cannot represent the multi-valued function, as we know. So they could go only up to this point, okay? And since we use the Hodograph transformation, we can go all the way up to the maximum wave amplitude. So it turns out that our results are very good in comparison with the previous works for small amplitude waves. And then, of course, once again, we have the evolution code. So we put the unstable normal mode and then let it evolve. And so here we put a very small the perturbations, which you don't see it. And then as time goes on, they grow like this. And they grow with the right growth rate that the numerical solution predicted. And at this point, when I go back to physical domain, then this is what happens, okay, at this time, at t equals to 100. So little perturbation, okay. So the next question is, what happens, if you keep run, this model, okay? All right, so that's something that we have to do, and I'm out of time. So we did, we play with similar, the evolution equation for other problems, like finite depth. Oh, sorry. These are the open questions, okay? First of all, we looked at the infinite depth problem. What if I have a, finite depth? Capillary waves. And then, which means, basically I'm looking at capillary jet, symmetric capillary jet, right? Because I have the bottom, which is the axis of symmetry. And also, as I said, what happens, if I keep running the unstable mode? We have some results, but I'm not going to talk about that. This is a really hard problem. What's going to happen to 3D perturbations? For small amplitude case, we can do what Chen and Safman did, do the Fourier series. But for large amplitude cases with the bubble, it's not easy to do. And I don't have an answer to this question, okay, yet. We play instead of Hodograph transformation to solve different problems, like gravity waves in uniform shear flows, and so on. I just skipped that. Okay. All right. So this is a summary of my work. We looked at linear stability analysis of Krapper solutions for both, subject to both superharmonic and subharmonic perturbations. And we confirmed our linear stability analysis results with the time-dependent simulations. So kind of we believe our numerical results, stability analysis results. And actually, in Korea, actually I'm supposed to come back next month to New Jersey. But before that, I want to do some experiments. And I have a small lab in Korea. They provide me some lab so that I can play with. And so we built a small tank to do laboratory experiments. The question is, what am I looking for? Okay. I don't know, to tell you the truth. But one thing is we can check the growth rate and that kind of thing. Okay, but actually I don't know. Roxana wanted to do some laboratory experiments, so I said, oh, why don't you build a small tank and so on. We have a high-speed camera and all fancy things. So we'll do some experiment, but I don't know what I'm looking for. Probably some modulation is unstable, so probably I'm looking for capillary log waves, if I can find. Then I'll report. But the real, the problem that I'm interested in is interaction between, gravity-capillary waves, and in particular, parasitic capillary waves. And this is some This is some simulation that I did, putting, gravity and surface tension at the same time. And you see the little wiggles. That's what you typically see in the ocean. And these waves are important for remote sensing because these short waves are, are resonant with, the electromagnetic waves. And therefore, the understanding of this part is important for real applications of remote sensing. So this is what I'm going, to in a few years. So anyway, thanks for your attention.